Now let's take a look at some boundary conditions, a fairly important topic. It turns out that if we have a wave that's going to be reflected off of say a surface, it's going to behave differently whether it has a fixed end or whether it has a free end. Consider this wave in scenario A where it's fixed to the wall. You can see it right here. The pulse is going to arrive at the wall, and you can even kind of think of it as the wall absorbs it for a little bit. The wave has momentum in the downwards direction here, so when the pulse is essentially spit out of the wall, it's going to be inverted as it moves away from the wall, and it's going to have the same amplitude. If you think about it reflecting off of a free end, here we have the pulse, and it's going to be say a ring on a frictionless bar. The pulse is going to arrive, and it's going to pull the ring upwards. The very last piece of this pulse is going to be pulling this ring in the downwards direction. So the ring is going to move in the downwards direction, and the pulse that's going to be reflected is not going to be inverted. So that's the key difference between a fixed end and a free end reflection. This will be very, very important when we talk about interference of waves and standing waves. Now suppose I have more than one wave on a string. What's going to happen? I mean, suppose I have a pulse right there and a pulse right here. This pulse is moving in that direction, this pulse is moving in that direction. Then these waves are going to interfere. They're going to essentially overlap. How the rope is going to behave is going to be called the principle of superposition, which says when two or more waves overlap, the total displacement is going to be the sum of the displacement of each individual wave. So you can see as these waves approach this middle point right here, the rope is going to barely move at all. This red wave is going to be pulling the string in the upwards direction. This blue one is going to be pulling it in the downwards direction. And the net result is the rope is not going to move very much at all. As the waves move away from the center, they're going to simply continue about their merry way. This has a very special name. It's going to be called destructive interference. If we now consider two pulses that are both in the positive x direction, and they're going to be approaching there, we can see that both of these pulses are going to pull the rope in the upwards direction, and when they're both at the very center, it's going to be magnified, and the displacement of the rope is going to be twice that of each individual rope. This also has a special name. It's going to be called constructive interference. And again, much like before, as the pulses continue, they're going to more or less just go about their way and have no real memory of this incident. So the last slide, it showed two waves that were traveling in opposite directions and how they could interact with each other. It turns out that if we have more than one wave traveling on a string, which we pretty much always will, we can time them such that they will interfere with each other and create a standing wave pattern that's not going to move on the string. We'll show an example of this on the next slide. We'll have destructive interference where the waves are going to essentially cancel each other out. One wave will be pulling the string up, one wave will be pulling the string downwards, and we'll have constructive interference where both of the waveforms are adding together. They're both pulling the string in the same direction. Where we have destructive interference, we'll call those nodes, and essentially the string will not move. There'll be no motion. The exact opposite, where we have constructive interference, we'll have what we call antinodes, which is where the amplitude of the string will be the greatest. So the next slide we get to see some pictures of this. So here you can see some time exposures of standing waves on strings, and essentially what we have here is we're sending a wave out over here. It's tied down on both ends, and so it's reflected in the backwards direction right here. and it appears that the string is essentially standing in place. Now, if we time it just right, we can send out, we can vibrate the string, send out our waves at a frequency such that there will be destructive interference here and constructive interference here, and so the standing wave is going to appear much like you see in this photograph. Now, if we vibrate it even faster, we can have destructive interference at 2 locations and constructive interference in 3 locations and get a standing wave with 3 humps, and we can do the same thing and get it with 4 humps, 5, 6, 7, 8. Now, we will always have these nodes where there is no displacement from the equilibrium position at the 2 endpoints because it's tied down. We also have a node in the middle here, and we have antinodes wherever we have constructive interference. Since a string is fixed on a so let's take a look at standing waves and the relationship between wavelength, frequency, and the length of the stringed instrument. By necessity, we must have nodes at the 2 endpoints where the stringed instrument is going to be fixed. What that's really doing is that's limiting the wavelengths or the frequencies with which we can set up a standing wave on this instrument. The easiest possible way to do this is to simply have the 2 nodes at the endpoints and the antinode directly in the middle. This is going to be called the fundamental frequency or fundamental wavelength, right, a lambda 1 right there, with which we can set up a standing wave. We know that the speed of a wave is equal to the wavelength multiplied by the frequency. The speed of the wave is going to be what it is, so frequency and wavelength can more or less be interchanged here. What is the relationship of wavelength to length? Well, you can look at this wave that I've drawn here in red and say, well, I know that 1 full wavelength is going to be 1 complete cycle of this guy, so in red here I've more or less extended it out to 1 full wavelength. So the wavelength that we're setting up here is actually going to be twice the length of the string. The next possible way to do this is going to be called the second harmonic, or if you're into music, this will be called the first overtone. Again, we must have nodes at the 2 endpoints, and we will therefore must have a node in the middle and then 2 antinodes here. You can kind of see here that this wave is going to have a wavelength that's equal to the length of the stringed instrument. We can then go on to do the third harmonic, second overtone, fourth harmonic, third overtone, and more or less we can describe the wavelengths being related to the length given any of these harmonics, or overtones if you will, and the frequencies as well, simply knowing that the speed of the wave is equal to the wavelength multiplied by the frequency. So very important equations to keep in mind for this particular chapter. We can also see that all of these possible frequencies are simply going to be the individual number, which harmonic we're talking about, multiplied by the fundamental frequency, at least for a string. Now that we know the relationship between the frequency and the length of an instrument, you can more or less see how longer string instruments are going to produce lower frequencies and shorter instruments are going to produce higher frequencies, simply because it's related to the length here. Now, the way that we tune a string instrument is we adjust the speed of the wave that is on that. We know that the speed of the wave is going to be equal to the tensional force, or just the force really, divided by the mass per unit length. We know that a string instrument is going to have different massed strings on there. So really what we're adjusting when we tune it is we're adjusting the force, the tensional force right there, changing the speed of the wave, which is therefore changing the frequency of the wave.